Hello and welcome everyone to the second entry into our IBDP CAS project series on mathematics. Uh, as foreshadowed in the prior video, in this one, I'll be focusing on imaginary numbers and complex analysis. However, again, this will not be a technical education on the topic, but rather a bird's eye point of view, which will illustrate the topic in a clear and concise conceptual manner for people who are not acquainted with it and do not have a technical education or are interested in mathematics from a layman point of view. What we'll be looking for in this video specifically is why we have imaginary numbers. Given that they're called imaginary, so I imagine that a lot of high schoolers and so on, when first faced with this concept, or were confused as to why they're learning about something that is literally called imaginary and hence to one extent or another non-existent. There are two ways we will answer this question. The first one is looking into their origin, so the historical why, and their applications, or the why in terms of purpose. However, before we move on to that, I will introduce reintroduce some concepts regarding imaginary numbers so that it is all obvious what I'm talking about. So, since within the set of real numbers, one cannot take the square root of a negative. An imaginary number is defined as a multiple of the imaginary unit I, wherein I is taken to be the square root of -1. So imaginary numbers would be 8y, 5y, -6y, -6i, and so on. Now, a complex number is a number that has both a real and an imaginary component. For example, 8 plus 2i. These can also be notated or otherwise represented geometrically on the so-called Argand plane, or also known as the complex plane or the Gaussian plane. It's a version of the Cartesian plane of coordinates, where instead of an x-axis we have the real axis, and instead of a y-axis we have the imaginary axis, in English literature typically denoted RE and IM. And here, any given point is a given complex number. So, for example, if we wanted to look for 8 plus 2i, the example I gave before, we'd have 2i on the imaginary axis and 8 on the real axis, and it's the point here. Now, there are a lot of rules regarding their operations with complex numbers and so on, but they're not necessary for the topic of the video. However, one thing I will mention is that they can be represented polarly, that is, using the modulus of the complex number, which, since a complex number is denoted z, is usually denoted using the absolute value brackets like this, and the modulus is basically the hypotenuse of the triangle with the imaginary unit taken as the opposite side and the real component taken as the adjacent side. And in polar coordinates, it's a complex number is the modulus and the angle of the modulus relative to the origin. However, that is only a side note. Now we will move on to answering the question at the heart of this video. So, why do we have imaginary numbers? In the 16th century, mathematicians such as Girolamo Cardano and so on found a way to solve cubic equations, which are equations which involve x to the third power or x cubed. However, only in those cases where they could be reduced. By this, I mean solved solved through simplification into equations that were essentially only quadratic. However, in some cases, such as this equation, solving them through this way was simply not possible. And this was called in Latin the casus irreducibilis, or the irreducible case. And the imaginary numbers enter the discourse here because similarly to when we can determine the solutions, if they're real or not, to quadratic equations using the discriminant, a cubic equation also has its own, which is way more complicated. And basically, for equations such as this, the discriminant predicted real solutions, but to get there, these 16th century Italian mathematicians had to take the square roots of negative numbers, and hence they introduced the unit I eventually. And this is why we call them imaginary numbers, because Rene Descartes, the same person who was a philosopher and is famous for his oft quoted statement that I think therefore I am, considered them nonsensical, and he called them imaginary as an insult, which eventually simply stayed as the term used for them. So they're definitely not imaginary in the sense that they're mathematically useless, because they actually exist for the solution of equations such as these. However, are they imaginary in the real world or not? Do they have applications? And for this, we go into the second half of this video, which focuses on complex analysis and its applications, which is the why in terms of purpose and not of origin. Now, complex analysis is analysis done on the complex plane, which we mentioned before. And analysis simply means the operations of calculus investigated at a mathematical rigorous level. So stuff like differentiation and stuff like differentiation, integration, and so forth. However, done within the complex plane. And this field finds many applications in real life, including physics, where it's used everywhere from quantum physics to electrodynamics, where it's used in the computation of circuits, and so on. And this gives us its application in engineering. And moreover, the complex numbers are also used in areas such as software design and related fields, for example, video game graphics, and so on. Which means that despite being called imaginary, they do indeed have a real meaning in the real world, as they're used for many of the things we see around ourselves, making them contrary to their originally an insult that became a name, very real and non-imaginary in the way we deal with the world, as many parts of our scientific comprehension of it rest on the imaginary numbers and complex analysis that derive from them.